Let's continue with the second part of our BMS communications module. Here we will be focusing on the external communication protocols and also in the wireless BMS concepts. We will begin by revisiting the fundamentals of the external communications. We will cover what are the key functions and common communication methods, like for instance CAN or automotive Ethernet. And then we will move on to explore the wireless communications in the battery management system. By the end of this section, you should be able to have a clear understanding on how the data move from the battery system to both the internal and external other systems that are in the vehicles, and also how wireless approaches are changing the way that we design and that we manage these systems. So let's start with the external communications. The external communications will allow the BMS to interact with several critical components that are in our systems. For instance, it will allow us to communicate with the vehicle control units. These are the units that manage the vehicle functions, that includes the power distribution, the energy usage of the battery, and the performance optimization of the whole vehicle. We also communicate with the charging infrastructure, and this allows to have proper charging protocols and to optimize the battery lifespan and safety. We will communicate as well with diagnostic tools, for instance. These are going to be all the external systems that will help us to monitor the battery performance and to diagnose any eventual problem, as well as to troubleshoot issues proactively in our applications. And the BMS can also communicate with cloud-based platforms. Modern BMS solutions often include remote monitoring capabilities. In these cases, all the data is going to be sent to the cloud and servers for analysis, for having predictive maintenance, and maybe even to have a fleet monitoring of many of these vehicles that are in the roads. As we dive into the external communications, we will be looking on how the BMS shares information and how the BMS will coordinate with other systems that are outside its immediate environment or the immediate battery parameters. There are three major points that will come or major functions that come into play. First, we have the data sharing. The BMS needs to send out critical parameters like the state of charge, the state of health, and the diagnostics information to various external devices and systems. This ensures that other elements that are in the network can take proactive actions, for instance, adjusting the charging strategies or alerting different services and teams in the bus. The BMS external communications also have functions in the system control. The BMS will communicate with the vehicle controllers, with the charger, even with remote user interfaces. And all of this will allow the devices to issue the commands, for instance, when to start, when to stop charging, and how to handle the battery pack protections. And finally, we also have the remote monitoring. In many modern setups, real-time monitoring can happen from anywhere, and the BMS can send all this data, as I mentioned, to the cloud, for instance, to have centralized control and to enable advanced analytics and predictive maintenance on the system. The BMS in these cases will typically rely on very established protocols, for instance CAN or local interconnect networks, LIN, or automotive Ethernet, because of their reliability, the compatibility, and the standardization of all of these protocols in the automotive industry. Each protocol will have unique characteristics, which we will explore next to see how they meet different data speeds requirements and how we can analyze each of those separately. So let's start with the controller area network, or CAN. This is really a workhorse in the automotive sector. It is very well known because it has an incredible ability to handle real-time communications in harsh and noisy environments. So think of it as a robust conversation channel when multiple nodes and multiple elements are communicating using the same bus, the same infrastructure, and often each of these multiple nodes are called either master or slave. The interesting thing of CAN is that all of those can talk in the same channel, but only one node speaks at the time to avoid conflicts between them. BMW was the first company to incorporate CAN communications, and by doing that, it reduced significantly the weight in the vehicle because it simplified a lot all of the connections in the communications and reduced also the number of connectors, physical connectors that were needed. Nowadays, the CAN communication is a standard in the vehicles, and new companies have even incorporated in other products, for instance, in drones, in e-bikes, in industrial applications, and even in elevators are starting to use CAN. The protocol is composed by two lines. We have CAN high and CAN low. In this case, one line is an inverting line and the other one is a non-inverting line. And in this way, we can use both to get a differential signal. So when we compare them and when we analyze them, for instance, in an oscilloscope, we can see that they are opposite to each other, and that plays a very important role in the noisy environments. Some of the strengths that CAN communication protocol has is that, first of all, the reliability. CAN has built-in detections and retransmission features that keep the data loss to the minimum. Also, it allows a multi-master architecture when each of these nodes can initiate communications, and this allows a very flexible data exchange. It is very easy to integrate CAN, and is so well known and so widespread that automotive components can be easily designed to plug and play on the CAN bus. Some of the disadvantages or the drawbacks of this communication is that it has a speed limitation. Classic CAN goes up to 1 megabytes per second, and there is a special CAN FD that can reach up to 8 megabytes per second, but this is not enough for many heavy data-heavy systems. Also, CAN has a very complex arbitration. It means that deciding which node gets the priority for communicating and when each of these nodes are allowed to send messages or not can be very tricky in large and heavy loaded networks. That's some other of the issues that CAN may have. Now let's take a closer look at another communication protocol that is the RS485. This is also widely used for external communications, and particularly is very well known in industrial and embedded applications. This is robust serial communication protocol that is designed specifically for long distance data transfer, and as similar to the CAN, is also very reliable in electrically noisy environments. Unlike CAN, which is tailored for automotive sector, the RS485 is a more, I would say, general standard that is commonly used in industrial battery system, in industrial applications, in energy storage applications, in distributed control systems, and in all of these applications where the communication needs to travel very long and extended distances. Here now let's put into the table some of the key points to keep in mind on this communication protocol. In the advantages, one of the most interesting, as I mentioned, is that it has an excellent noise immunity, and this allows it to work in very long distance. Similar to the CAN, this protocol also uses differential signaling, and this helps to minimize interference in electrical noisy settings, making it a very, very solid option in those systems that spread across wide distances. Also, it has very simple hardware and is very flexible to use. It is cost effective, and it is doesn't require very sophisticated transceivers or very sophisticated equipment to communicate. You can connect many of these devices on the same line, and this can be very beneficial when you are building distributed systems. On the downsides, however, we have that this particular protocol does not offer standard protocol layers. What does it mean? It means that you often have to implement your own way of framing the messages, handling the errors, and detecting problems. It is an application that you have to build, and it is not standardized, as it was, for instance, with the CAN communications. Also, as it might achieve very long distances, it is specified that it can go up to 10 megabytes per second in very in short distances. The problem is that it has limited speed at high distances, so the speed will drop as we increase the distance in our communication bus. Also, as it does not have any built-in arbitration mechanism, you need to be careful on how multiple devices transmit the data to avoid collisions and losing information in that way. Overall, to summarize it, this protocol is very interesting because of its affordability, reliability, and very important when you are trying to deploy across longer cables. And then we have the automotive Ethernet. This is another external communication protocol. It's very interesting, this one, because as the vehicles become more intelligent every time, and when we are trying to package advanced driver assistance systems, high computing power, and even multimedia features in the communication within the vehicle, because they are getting smarter, the traditional protocols are maybe lagging on the bandwidth and on the speed that is required. Because of that, the automotive Ethernet has taken a very important role in the automotive communications nowadays. It is a specialized version of Ethernet, but it is optimized for automotive conditions. Some of the key features of it is that the speed is very high, and it can vary from few 100 megabytes per second to multiple gigabytes per second. And this is ideal for transmitting very complex data like sensor readings for autonomous driver or infotainment into the screens of our the vehicle and so on. Also, the automotive Ethernet standard ensures a very robust performance. It has low latency. It is crucial for safety critical tasks, for instance, in avoiding collisions and so on. The problem and the disadvantages is that the hardware and licenses fees are way more expensive than, for instance, CAN or the RS-48, and that makes increases also the complexity in the system. To proper setup and to do maintenance of this particular protocol requires very trained personnel, which can increase the operational overhead, and also is very use case specific. For low data applications, the expenses are not justified. Only it makes sense to use automotive Ethernet when we really need to transmit high volumes of information and very high, and when we require very high speed data transfer, in those cases, the automotive Ethernet becomes a top choice. We will shift a little bit the discussions and we will explore how the battery management systems can communicate without the wires. All of the protocols that we mentioned before, the internal and external protocols, rely on electrical connections and wires to transfer the data. But in this section, we will discuss what makes wireless BMS different and why this wireless BMS is gaining traction nowadays, and where it is also some of the advantages and disadvantages compared to the wired counterparts. So let's see what wireless BMS is. Okay, so wireless battery management systems, it's a new trend that is evolving very fast. And basically with these trends, we are changing the way that we manage and we monitor the battery packs. Traditionally, the BMS units connect the sensors and all the hardware that is connected to the BMS, all of it is connected via wired harnesses. However, the wires will add some weight to the battery, and this can be challenges to install also, and at some point will add some vulnerability to our system. The key concept of the wireless BMS is that instead of relying on physical connections, a wireless BMS will leverage the radio frequency protocols to gather the voltage, the temperatures, and all of the critical parameters, reducing the number of cables that are going to be needed and simplifying at the end very specific aspects of the production and the maintenance. There are different protocols that you might see in the integration of wireless BMS. We have, for instance, Wi-Fi, Bluetooth Low Energy, Zigbee, NFC, and even cellular networks for broader coverage can be used in these strategies. Each option will have a trade-off between the power consumption, the data range, the range itself, and depending on the architecture of the wireless BMS, we will decide for one or for the other. So when we are transitioning to a wireless BMS, we can choose, as I mentioned, we can choose from several popular protocols that are used already to implement wireless solutions. One of them is, for instance, the Bluetooth Low Energy. This particular protocol is very useful in short range and low power tasks. It is interesting because as we are trying to monitor batteries have a limited amount of energy and we should try to optimize as much as possible. So to use communication protocols that do not require high energy consumption are going to be prioritized in this type of products. Bluetooth Low Energy is already in millions of consumer devices and making this very easy to integrate, and it is very good, for instance, to connect our battery to smartphone apps and to check the battery status and so on, but also it can be used for creating networks of the batteries modules or the battery cells for sharing the information between all of those. Another one that we have is Zigbee. This is known for its mesh networking capabilities. So if you have multiple modules or multiple nodes that need to relay information across a relatively wide area, Zigbee provides a very stable low power operation. And then we also have Wi-Fi that will offer a higher bandwidth and can cover larger distances, but is a little bit more demanding on the power requirements. So the energy consumption has to be managed very carefully. These are some of the solutions, but there are many other protocols that can be used to implement the wireless technology. So to conclude with this part, let's compare how wireless BMS relates to the more established wired solutions. And let's see what are the different advantages and disadvantages of each of these solutions. Some of the advantages of the wireless BMS, the first and the most important is the lightness. When we remove the cables, we can cut the battery pack weight by up to 15%. That's a substantial gain for the energy vehicle because it will overall improve the efficiency and will extend the range of the vehicles by having lighter batteries. Also, we will add flexibility because adding or replacing modules is going to be way much easier since they are not going to be tied to a physical wiring layout. This is very important in the manufacturing process when we are servicing and when we are planning to put future upgrades in our battery systems. And also the safety in manufacturing and in services is I guess improved as we have fewer cables and fewer connectors. We will reduce the points of human error and potential hazards during assembly or maintenance because the assembly process will be simplified. The disadvantages is, or one of those is the data security. Wireless transmissions can be intercepted, and if they are not very well protected, designing they can be it can be a lack of security in the process. So what we need to do is to design the communication with advanced encryption methods as well as authentications to be sure that the information that is being sent is going to be protected. And also another disadvantage is that the design complexity will increase in this type of systems. Wired BMS are very mature technologies, they are very well understood, and there are standards and best practices for this in the industry already available to implement easily. Wireless systems require new technologies and to advance into the research and the development of these solutions. So it makes a little bit more complicated to implement these systems and to ensure their reliability. Ultimately, the choice between a wired or a wireless BMS will depend on the goals of the performance, the cost, the reliability, and the weight reduction that we are aiming at the design of our battery. Wireless BMS is still evolving, but it has a lot of potential to simplify the vehicle design and also to enable new functionalities that I think they're gonna be sooner adopted by the industry.